Welcome to IT Pro TV. I'm your host, Don.
Coming at you live from San Francisco, California.
You're watching IT Pro TV.
Hello and thank you for watching IT Pro TV, helping you learn wherever you go. I'm your host, Zach Memis, as we continue on with compTIA Net Plus. This is Routing Technologies, and Wes Bryant is here to help us out once again because he's an awesome guy. Wes, great to see you. Thanks for being here.
Hey, thanks, Zach, for having me back. That's right. We are moving along in really domain 1.3, that is routing and switching technologies, right? So in this episode, we're going to be looking specifically at the routing technologies, just like Zach has said here. So let's go ahead and dive right in. You know, in other episodes, we've talked about some of the layer 2 technologies. We talked about switching technologies and some of the characteristics of switching technologies. But now we're moving up the OSI model, right? And we're moving into layer 3, right? So when it comes to routing, remember routers in general, they are our smartest connectivity devices. Remember, we've talked in other episodes about network devices. We've talked about a hub and how a hub is really a dumb device. It's the dumbest device that we have on our networks because it doesn't understand logic, right? It sits down there at layer 1, it just receives information on its ports and it just electrically sends it out all other ports, right? Then as we move up the OSI model, we have our layer 2 connectivity devices, right? Our switches. Our switches, they operate on MAC addresses. But remember that a switch, even though it's intelligent, right, and much more intelligent than a hub, it still has a limitation in the fact that it's only aware of the devices that are directly connected to its ports, or if you're doing VLANs, aware of devices, you know, other switches that are connected to it. But you have to be directly connected to the switch in order to send traffic between source and destination when we're talking about switching technologies. Here in routing technologies, however, routers are the most intelligent connectivity device that we have, right? Because they can make very complex decisions, right? They have to have a lot of computing resources. They're essentially a dedicated high-speed computer, if you will, that uses all of its resources, CPU and RAM, if you will, in order to calculate what is the best path to send our information. Now, even more so than that, compared back to a switch, a router doesn't have to be connected to a network in order to get the traffic there. And when you say, well, what do you mean by that, Wes? Well, routers really are what allow us to communicate across the internet. If it wasn't for routing technologies, right, if it wasn't for those layer 3 technologies, we wouldn't be able to send information to distant networks. So routers can do some very cool things in the fact that they can actually communicate with amongst each other and say, hey, I'm not aware of that route. Here, what do you have? And then they can inspect the information that another router sends them, and they can say, oh, okay, I see that there's a route here that I wasn't aware of. Let me go ahead and put that in my entry, right? It would be, for instance, let's say that, you know, I was taking a trip from point A to point B in my car, and I've been taking that trip, that path, if you will, for, let's say, the last few months. And I asked Zach, I said, Zach, have you ever been to destination B? And he says, yeah, Wes. He goes, I take this way. And I say, well, you know, how long does that take you? Well, it takes me about 15 minutes to get there. And I'm like, well, Zach, the way that I've been doing it for the last 2 months has taken me about an hour. Chances are I'm going to just go ahead and forget the way I was going, and I'm going to take your advice, and I'm going to go the shorter path, right?
Which is the smart plan.
Exactly. So that's kind of what routers can do, right? Routers can communicate amongst each other, and they can learn of what the network topology is, and if they find a better path, they can say, well, I don't want to take the long way around, right? So let me go ahead and discard that path that I'm aware of, and let me go ahead and update my information here, and I'll send information to that destination based on that better choice. So that's a little bit about your routing technologies. Now, and what the routers are doing. Now, they do a lot more than just that. Yeah, they're really intelligent, but for the basics, that's what's going on, is that a router doesn't have to be connected to a network in order to get information there, and it's really what allows us to communicate. It's what allows your local area networks to communicate amongst each other and really across the internet. So let's go ahead and let's dive into some of the technologies that allow us to route traffic across networks. One of the first things that we have to talk about are protocols, all right? And more specifically, routing protocols. See, IP, we talk about IP addressing. Routers make a decision on where to send traffic based on IP, based on the Internet Protocol, the addressing information. And now we're talking about layer 2 or layer 3, right? So we're talking about IP addresses. And routers use protocols in order to determine what the best path is, because IP it's responsible for our addressing. It doesn't make any decision on how to get the information there. In fact, all it tells us is what the destination is and what the source is too. And it's in combination with routing protocols that the routing protocols, depending on which ones we use, will talk to the other or allow us to discover the topologies. And there are a few different types of routing protocols that we have to be aware of, but largely speaking, they can be classified under two different categories. And I've got a little diagram here that we can kind of talk about this, right? We have what are known as interior gateway protocols, and it looks like I need to adjust my slide here on the fly here and spell right. We have what are known as interior gateway protocols, and we have what is known as exterior gateway protocols. Now, when we talk about interior gateway protocols are what are used inside of your networks, right? Inside of your autonomous systems, and they're responsible for passing traffic inside of that network. Now, they call them interior gateway protocols because they don't share the information that is communicated amongst them with other autonomous systems or other networks. Now, an autonomous system, what do I mean when I say autonomous system? Well, what I mean by that is that an autonomous system are essentially what you have, the networks, the local area networks that are across the backbone of the internet. Now, please understand that inside of an autonomous system, you can have multiple local area networks. It just means that that network is under the control of a single administrative body and it adheres to a certain routing protocol. Like, for instance, Apple has an autonomous system, but I can guarantee you it's not just one small little network. It's a bunch of big networks, but Apple controls it, right? So know what autonomous systems are. Now, what I mean by interior gateway protocols is inside of those autonomous systems, they don't share information across autonomous systems, right? That's why they say interior. It's inside of your network, right? And that's in contrast to what's known as an exterior gateway routing protocol or exterior gateway protocol. And these are protocols that essentially, I say protocols, it's really only one that we use largely today. This is a protocol type that allows us to share that routing information between autonomous systems. It's how your internet service providers actually move traffic across the internet, across the backbone of the internet. They do it with what's known as exterior gateway protocols. Now, you're going to see that I've got some examples here of interior gateway protocols, right? We have what's known as RIP, and I've got RIP v2 because, and we'll talk about why that is. RIP was the earlier routing information protocol, and that's actually in your exam objectives. But we want to talk about routing information protocol and its successor, routing information protocol version 2. That's an example of an interior gateway protocol. Now, we also have OSPF, and we'll talk about it as well. That's another example of an interior gateway protocol. It's one of the most common routing protocols that are used inside of your internal networks today. And again, we'll come back and we'll give you some more characteristics in a second here. And then last but not least, we have the exterior gateway protocols as well. The exterior gateway protocol, we really only have one that we use, and that's one known as the border gateway protocol. And we'll dive into that a little bit more too, and I'll tell you why it's called a border gateway protocol. All right, so that is a little bit about, and the other thing that I want to mention too is that how they classify the routers. If you have a router that isn't sharing information across networks, it's interior using an IGP or an interior gateway protocol, they call it an interior router. Right? It's an interior gateway router versus a border gateway router, which is the router that's communicating with other routers between autonomous systems. So just a little bit of jargon right there to kind of get out of the way here as we move on.
Good, thanks.
All right, so understand that routing protocols, basically, they operate or route traffic between autonomous systems. Those are called IGPs, those are called EGPs. All right, so let's go ahead and let's dive into the very first protocol that we need. Now, when we talk about IGP, again, interior gateway protocol, and we talk about exterior gateway protocols, understand that your IGPs are actually divided into two subcategories, all right, or two categories themselves, right? So we have interior gateway protocols that we're going to talk about for a bit here now, and they're basically divided into two different types of routing protocol. One is known as a distance vector protocol, and then the other one is known as what is known as a link state protocol. Let's go ahead and just talk first, we'll talk about what's known as the distance vector protocol. All right, so a distance vector protocol is one that is using how does it make its choice, right? And that's really what we're talking about when we say a distance vector protocol versus a link state protocol. How do we make the choice of what the best path is? All right. Well, I gave you an example earlier where I was driving from point A to point B. I had been, it took me an hour to get there. I talked to Zach. Zach said, man,
15 minutes, folks.
That's
15.
Right. Zach says, hey, man, I got a better route that you can go to the same destination and it only takes you 15 minutes, right? So distance, notice distance here. The longer the distance, the longer the time, right? Time isn't really a consideration in this one, but distance, right? For me, in my analogy, time was a consideration, but it was the fact that Zach gave me a shorter distant route, right? So I chose that. And that's how your routing information protocol and more importantly, your distance vector routing protocols work, right? Vector is just the destination. So we all, and that's what routing is about, right? The destination. How do I get it to the destination network? So vector is destination. Distance is how we're making the choice of what the best path is, all right? Now, what do I mean by that, right? Well, that's, there's another topic, if you will, concept that is associated with routing, and that's something known as a metric. All right, my metric that I told you was Zach happened to be time for me. I said, hey, my metric was an hour versus 15 minutes, right? Well, for me, the metric, it can also be considered a cost, right? How long was the distance, right? Well, how far the distance is the cost, right? Think about saving you gas, right? I could drive from point A to point B. It takes me an hour. It takes me a lot more gas money. It's a higher cost, right? If I take the shorter route, right, Zach's example there, then I only drive 15 minutes. The cost is even lower, right? So that becomes what I would consider the best path based on its cost. Now, what would the metric look like if we're talking about a distance vector routing protocol? Well, it's based on hop count, all right? So if we take a look here, I've got routing information protocol, and as we go through this, we'll kind of talk about some of the things that you have to be aware of when you talk about routing information protocol. All right, let's take router 1 here, all right? Router 1, we've got router 1, router 2, 3, and 4, all right? So if we're using a distance vector protocol and router 1 needs to send information, let's say, I tell you what, let's go ahead and let's put a little cloud out here and we will say that, hey, this is the network that we need to go to. All right, so this is the network that we need to deliver traffic to. We'll say network A. All right, so network A, router 1 has to figure out how do I get that information. Router 3 just happens to be connected to that network. All right, now, when router 1, if using a distance vector protocol, router 1 is going to take into consideration what the hop count is. All right. So what we mean by hop count is the art of forwarding traffic from one router to the next router. And you can see if I forward traffic between this router and this router, essentially what we have is we have a hop count of 1. All right, so that's the art of forwarding traffic, if you will, the process of forwarding traffic between one router. And if it goes across one router, that's 1 hop. Across the next router, that's 2 hops. And then to this router is 3 hops. So we end up having 3 hops overall. That is how we're going to make our choice, right? The shorter the hop count, the better the path. So if we have to say, all right, well, it's essentially 4 hops. Oops, I don't know what's going on there. Sorry about that, guys. Try to zoom in there, give you motion sickness. So if router 1 has to get to network A, notice that we have 3 hops here because we're going through across 3 different connections, if you will. And then we have to go from router 4 to router 3. Notice that we have, again, 4 hops here. 1 hop here from this router, obviously all the way down till we get to this network. Notice that we end up having 3 hops and 4 hops. All right, so that's a total of 7 hops to get to that network. But if router 1 sends the traffic to router 2, we've got 1 hop here, all right, from this router to this router, and then from this router to this router, router 2 is 2 hops. And then we have from router 2 to router 3, we've got 3 hops, right? So again, the art of forwarding that traffic between 2 routers. All right, we have 3 hops. That's a total of 5 hops. So notice that when this router has to make a choice on how to get to network A, it's not going to use this path because this path is 7 hops, where this path here, 3 and 2 is 5 hops. That would be like Zach's route versus Wes's route, right? Wes's route took an hour to get there. Zach's a little bit less time, right? That's a lower cost. All right, think it is like your gas money, right? It's going to save me a lot of time and money going across the shorter path. And that's how RIP and RIP version 2 make their decision on where to send the traffic. All right, so that is a basic on how routing information protocol is making its decision. Now, I want you to know that this is, it's a long-running protocol. All right, RIP, if you will, by itself. Another one of those oldies but goodies, like we've talked about other protocols, Telnet, if you will, and FTP. Been around for a very long time. Goes all the way back to the days of the ARPANET, right? The Advanced Research Project Agency. Prior to it becoming the internet, the military owned it, and it was only the military and universities were on that network. That's how old it is, all right? It's not a very scalable routing protocol, and the problem is because of how it communicates its routing table. All right, it's really used in networks that we're talking about the same type of routers, and it really only scales up to around 20 to 30 routers. Anything more than that, we start to get problems. And what it does is, and if we can go back to my slide here real quick, these routers talk to their neighbor routers. All right, so router 1 communicates with this router and this router. It doesn't communicate with router 3. All right, and then this router here communicates with this router and router 1. But it doesn't communicate with this router, all right? So we're only talking about the neighbors, right? Who am I directly connected to? I'm gonna talk to Zach, and if I had somebody on my the other side, I would talk to them, right? But I'm not gonna talk to anybody beyond that, all right? And what it does is it sends out what are known as RIP response messages. Routing information essentially is shared between these neighbors every 30 seconds, 30 to 45 seconds. And what's interesting about that, and kind of the drawback is, let's say that, let's say Zach, I'm going to say Zach is a router, and we're communicating. We need to share information, right? Kind of like Zach did with telling me a better route that could have saved me a lot of time had I listened, right? We're going to communicate that information between Zach and I. Well, what if Zach sends me a routing table every 30 seconds and nothing has changed? Well, I'm receiving information that technically I don't need. So we're still going to be giving information out, even if nothing changes, even if the topology never changes. So that can be a problem here. Now, we also have something known as convergence. Notice that this router talks to this router and this router, but it doesn't talk to router 3 down here. So in order for and let's say a link goes down, all right? Let's say just randomly this link goes. Well, router 3 is only going to be made aware of the fact that that link is down once this router communicates with this router, then this router communicates with this router, likewise down the chain until finally that information makes its way around the network and gets to router 3. Well, that's a process known as convergence. All right, convergence is the process, if you will, or the time that it takes for a topology to change, like for instance this link to fail, and all of the routers that are using RIP or RIP version 2 to be made aware of it. Convergence just, if we have a converged network, it just means every one of these routers have an updated information. They know what the current topology is. But we can see that in only talking to our neighbors, it's going to take a little bit of time before this guy talks to this guy, likewise down the chain, and that information gets over to router 3. So it's a very slow convergence time, right? And that's one of the problems that can happen with this. You want to be made aware of a topology change immediately. So again, one of the drawbacks, I'm going to be giving Zach information, Zach's going to be giving me information, even if routing topology doesn't change, but because we're only talking to the neighbors, when something does change, it could take a while for that change to propagate across the entire network, which also leads itself to layer 3 loops, right? Routing loops is when we have bad information, right? If for some reason this link goes down, router 3 hasn't been made aware of that information, the fact that that link's down, right? And it could try to keep sending information into this bad route around this path, and then when it gets to this router says, I can't talk to router 1. Let me figure out how I can talk to router 1. Well, I learned through the grapevine that this router said, hey, yeah, I could get that information to router 1, and it goes back this way. Finally, back around the chain. So you can start to get things like routing loops, and you can get very, very slow convergence time, so that's a problem. The other thing that you have a problem with, too, is that it has a maximum hop count of 15, Anything more than that, 16, means the destination network's unreachable. So it can't scale past 15 hops, right? So again, it's not a very scalable routing protocol. Now it also has, it had problems too. It couldn't handle variable length subnet mask, VLSM. Routing Information Protocol did not have that functionality or feature. So they tried to update or upgrade Routing Information Protocol. So they came out with Routing Information Protocol version 3. The other problem is, how can I tell that that's Zach? All right, now physically I can see that it's Zach, right? But I need to be made aware that somebody didn't just jump in Zach's place, right? And now is handing me bogus routing information, right? That could just cause problems, could disrupt my network, and for security purposes cause problems. So what do? All right, I give Zach an ID badge, and when he goes to hand me information, before he does, he hands me an ID and says, "Hey, I'm Zach," and I can inspect it and say, "Oh, okay, yeah, I see you, Zach," even though we can see Zach, right? Well, you didn't have router authentication in RIP, so you could have the potential for unauthorized information to be shared with a neighbor. RIP version 2 comes out, you have router authentication. It means that my neighbors are going to confirm who they are before I accept their information as valid, right? So you also get authentication. Also multicast communication, because one of the things that RIP was doing is broadcasting the routing tables every 30 seconds, whether there was a change or not. Remember what we've talked about in other episodes about broadcast communications. They can cause problems. So that was one of the problems with it. But even though RIP version 2 gives you support for variable length subnet masks, authentication, and multicast routing, it still retains its slow convergent times and the hop count limitations. We still have that 15 hop count limit. Anything, a 16 hop is the way you could say, hey, I don't want you to use this route, right? I could say, hey, this network, yeah, that's a 16 hop count, if you will, and that means destination unreachable, and it purges that entry out of the routing table. Now, the other thing that I didn't mention when we started about our routers and the routing table, that's that database of networks that the computer is aware of. One of the things that I do need to mention, it doesn't matter what the routing protocol is, you only have one route to any destination network in the routing table, right? We don't have two routes to the network. To the same network. It doesn't work that way. Because remember what routing is about, determining the best path. There's only one, it's got to be king of the hill. We're not going to share that, right? All right, so only one route makes it into the routing table for any given destination network. In fact, let's go ahead and log into our Windows 10 machine. Believe it or not, your operating systems also have, let me go ahead and clear this up, your operating systems also have a routing table within them. All right, now, the routing table that they have is the networks that they're aware of. In fact, let me go ahead and show you the routing table. We've talked about this, this command in other episodes. This is the route print command. And I'm going to just narrow this down by doing V4 so we can see the IPv4 routing table. These are the networks, if you will, that my computer is aware of. All right, and what we see here is we see the loopback network. All right, we typically, when we ping the loopback address, we ping the very first address within that loopback network, 127.0.0.1. But technically, the whole entire network range, you can see 127. 3 octets are reserved. The entire network is reserved for loopback processing. So it says, hey, here is the loopback network. I'm aware of that. Here is, and apparently one of my network adapters, I got 2 network adapters in here. One of them has an APIPA address, which if you don't remember APIPA, go back to DHCP. We talked about that, the automatic private IP addressing, right? 169.254.anything.anything. Well, in order to route my computer to send traffic over IP, or via IP, right? It has to know what the APIPA network is. So there we can see that it's aware of that. These are all default routes, by the way. These the routing table, these are built by the operating system. All right. This is the IP address of the local machine in the routing table, right? So I can see the, no, I'm sorry. That is the IP address right there. This is the network that this IP address is a part of. So if, for instance, if I do, let me go ahead and do an IP config so we can see that that right there is the actual IP address of the machine, and it's in the routing table. And if we run this, you can see, sure enough, by correlation there is the 172.16.184.137. All right, and we'll rerun that route print command, and this is the network that IP address is on, including the broadcast address, right? When my computer has to send a broadcast communication over layer 3, it has to know what the broadcast address is for that network, and it says I can find it right here in my routing table. Right, and then we also have the multicast addresses as well as the network broadcast address. But there you can see the routing table, right? And RIP version 2, back to our point within the routing protocols, this is how that table would be built within the router. Now that was an operating system's routing table, and it's generated based on the IP address that you configure on the machine, and then some of those just default routes that make it into the routing table. There is one other route that I want to talk about real quick inside of this machine, but we'll come back to that here a little bit later. Now, it does look like we've got a lot more concepts to go over, but it does look like Zach's giving me the old evil eye over here, telling me we might have run out of time on this episode.
Well, not so evil. Wonderful job, Wes. And this has been Routing Technologies Part 1. There will be a Part 2, so make sure you catch that and catch all the wonderful episodes that Wes has put together for you in the compTIA Net Plus series. And when you're in that course library, hundreds of other videos. They're all designed to help you go further. And tell everybody you know about IT Pro TV. IT Pro TV is binge-worthy. Thanks for watching. I'm Zach Memis.
And I'm Wes Bryan.
And we'll see you soon.
Thank you for watching IT Pro TV.